Hi guys. So far we were only implementing leave functions in assembly programs, and we were quite successful with that. We could write nice programs, but of course it's time to go one step further. We want to have functions that can call other functions. And for that we will use a stack data structure. In this video it's just about the principle. How can we achieve it, that we can call a function that calls other functions. And in the next video I will show you how also parameters and return values can be handled, and also local variables. In general, a stack data type supports two operations. Think of it as a stack of plates. You can put something on top of this stack, and you can take something from the top of the stack. And how can this help us for solving our problem that functions should be able to call other functions that call other functions and so on? Well, in the example that I will show you, we have several functions. The entry point will be this function start, and this function will call function main. And after this call, on top of this stack will be the return address. That means if function main returns, it just takes from the top of the stack this return address. But in the example, before that happens, function main calls this function foo, and that means another return address will be put on top of the stack. And if function foo would return, it would just take off the return address, which is at the top of the stack. But before that happens, function foo will call function bar. And that means another return address will be put on top of the stack. And then function bar will return. That means it takes from the top of the stack the return address and jumps back. And then also function foo returns, and so on. And that means in the end, the stack is again empty, and we're back in this function start at the return address, and then we will just halt the program. Of course, we have to think about implementation for this stack data structure. It should be efficient, and it should be specially dedicated to our needs, that we want to support functions that call other functions. For that, we will use a register for a stack pointer. And initially, the stack should be empty, and this will mean that the stack pointer points to the end of the memory, because in this area of the memory, we haven't used so far any memory cells, so lots of space is available there. What does it mean that it points to the end of the memory? Well, it means that we zero initialize this stack pointer, because we have 64-bit addresses, because we have a 64-bit virtual memory space. The address of the last memory cell would be 2 exponent 64 minus 1. And the next address would be 2 exponent 64. And because we have 64-bit registers, it means this is the 0-bit pattern. The push operation and the pop operation will be implemented with 2 instructions each. Push operation means that we first decrement the stack pointer. And because we want to store 8 bytes on top of the stack, we decrement it by 8. And then we store 8 bytes in this 8 memory cells. And a pop operation is just doing the reverse. We first fetch from this stack pointer 8 bytes. And after that, we increment again the stack pointer. And that means we do not clean up on the stack. You will still see the old return address. For the instruction set, it means that we need one more instruction. So far, we just have an operation for storing a single byte. Now we also have to add one instruction for storing 8 bytes. So first of all, I need a new instruction for storing 8 bytes. I will begin with a copy of the instruction set from the last session, and this variant will be called stack. And in this instruction set, I basically just have to make a copy of this store instruction for a single byte and change it to storing 8 bytes. So this was this move B instruction. And here, by the way, we also can provide an alternative where we also can specify a displacement. Could be useful later. Now, the last instruction here had opcode hex18, so this new instruction will have opcode hex19. I will add this comment for the documentation later, and this now becomes a move Q instruction, and it stores 8 byte. So that's it. I can regenerate the architecture, or generate it actually. And here I can begin with a proof of concept for function calls, where functions can call functions. Let's call it func. And I will begin as usual with some conventions. Compared to the conventions for these leaf functions, those will be much simpler. Only 3 registers will actually have some special meaning for this function call conventions. Register 1, 2, and 3. Register 1 in this example and this video actually will not be used, but I already want to specify this. This will be register 1, where the frame pointer will be stored. And in register 2, we will store the stack pointer. And in register 3, the return address. And then for demonstration purposes, I will also use always register 4 for storing the function address. But you will see that actually you can use all other registers in your functions. Just this register 1, 2, and 3 will have the special meaning. But I think it's kind of better to read and understand the concept if we give this registers that have some use, some special name. And so this will be, for example, register 4. And then we will begin here with the function start. So we have a label, and here we begin with the stack initialization. So we just store the 0-bit pattern in the stack pointer register, and then we will call this function main. And this comes later, and once we return, we will halt with exit code 0. Later we will halt with the return value of main. So for calling this function, I need an address of this function, and of course also that means that here I will have a label for this function main. And then I first have to load the address of this function into a register. I will just use our instruction for storing literal that can be represented with 16 bits. Of course, in the exercise, you should modify that so that you can load an arbitrary literal into a register using our pools. So the label is main, and this will be stored in func header. And then I have to store the return address on top of the stack. Now the problem is I will know the return address only after the call of this function, because our instruction for calling a function will store, when the call is carried out, the return address. So that means before this instruction, I do not actually already know the return address. And that's why I will split this push operation into 2 halves. I mean, we anyway have 2 instructions for the push. And the caller will do the first half, and the callee will do the remaining work, the second half, when the function gets called. So that means here I just decrement the stack pointer. Let's use a comment here. First half of this pushing of the return address. And when we enter this function main, then we actually have in this register the return address, and then we can complete this push operation. So the first instruction here will actually store the content of this register on the stack. And so this is the second half of this operation. And then this function can do whatever this function is supposed to do. So here we actually begin with the function body. And so that means here in between, we, for example, can print a character, let's say just the character F. And then here we are at the end of the function body. And after that, we have to return. And for that, I have to take the return address from the top of the stack. That means I need this fetch operation. I fetch from the stack pointer the return address and store it in this register. So this is the first half of the pop operation. And the second half will be done by the caller, so that we equally distribute this work of pushing and popping the return address. So here I just return. And then after this call, the caller needs to complete this pop operation. That means the caller has to increment this stack pointer. And maybe we also should print out some character to see that we actually did return. Let's say we want to print the character R followed by a new line. And that's it for a first try. So this should first print this character F, then this character R, and then a new line. Okay, seems to work. Now, in theory, it should be possible that main also just calls another function following the same pattern of how to call a function, and this function foo also should behave as function main, that it first completes the push operation and in the end does the first half of pop operation. So basically it means that we now can copy paste certain things. So for example, for calling a function, I just copy this block of code and change the label into foo. And this will come here after printing this character. And that's already it for calling this function foo. Now we of course also need this function foo. And for that I just copy here everything to the rest of the file. And maybe we can already be greedy. So this will be function foo. So I just change now main into foo. And here I already can call this other function, bar. So I just change this into bar. And then I copy this here again, and this should be it for this demonstration purposes. So this function bar will not call another function. But we somehow have to change this output so that we actually see the trace on how this function call graph looks like. So this is bar, this is also bar, and so here we just have to think about how to keep track of what gets called. So we first print this character F in main, then in foo we will of course print the character O. Then we go to bar, here we print another O, and then we go back And after this function returns, we will print a b. Then we return to main. After this function call, here we will print an a. And then we will return to start, where we will print an r. So it should print foobar, of course. And that's it. Now, of course, it's also interesting to see this stack used for the return addresses. And for that, we can use the debugger. Let's first increase the font size a bit. Of course, it will be most of all interesting to see how this return addresses will be stored on the stack. And note that currently we just have a virtual memory page for the text segment. And you will see that we will get a new virtual memory page as soon as we will store something on the stack. The first instruction is just initializing the stack pointer. So this is just modifying a register. So this has actually nothing to do with the memory. And then we load the address of this function into a register. Then we decrement the stack pointer. And then at address hex C, we jump to this function. That means the return address will be hex 10. And now we are in this function foo. Function main, sorry. And the first instruction will store the return address. And now you will see we get here a new virtual memory page. And the stack now contains this return address. And then we prepare the next function call. So we again decrement the stack pointer. And then we jump to this function. And then we store the return address. And the return address this time will be hex34. Here we go. And then we prepare the next jump. And now we will jump. The return address now will be hex58. And this return address is now stored on the stack. And then we are done here. We printed foo already. Then we take the return address from the stack, hex58. Then we jump back to this return address. Then we complete this push operation, increment the stack pointer. Then we print another character. So this should be B. And then we pop the return address from the stack. And then we jump to this return address. Then we again complete the pop operation. We print the character A. Then we get the return address from the stack. Then we jump back. And now we are basically back in this start function where we print this character R and the new line, and then we halt the program. So what's left to do, what's coming up next? Of course, we also want to use parameters in functions, and we also want to have return values. We will also use the stack for that, for storing these things. And we will also use the stack for local variables.